So what we're going to do this week is paired sample T. And there's a couple review slides at the beginning to kind of refresh on everything we've been doing. So I'm going to remake that table that we made a couple of weeks ago when we first started this section. But we'll just kind of rewrite it to get you back to where we're going. So what we did last time, so here's the test type. So when you have a z-score, try this one. You have one person. And so for the formula, it's x minus the mean over standard deviation. And then if I have a sample, single sample, third time's a charm with markers.
Sorry, Erin.
It's called a z-test. So more than one person. Now I have a sample mean minus the mean over standard error. Okay. So we know the population standard deviation. And then what we did last week was a single sample T. It's still one sample. But now I don't have the standard deviation, so I have to estimate it. So we can use SM or SE, either way. And so all we've been manipulating really, first one to second one is the number of people, second one to the third one is we don't know the population standard deviation. What we're changing today is one sample tested twice. And that's the new piece. There are going to be some more columns out here in a minute. So we're going to have a mean difference score, time 1 minus time 2, over standard error. So everything we've done so far has been one sample. Next week, when we do independent T, we'll get into 2 samples. And then we'll do 3 samples, and then we'll sort of change tracks. So the last test is not about samples, it's about continuous variables. So if we want to study either 2 groups or the same group twice, so we can go ahead and add independent T on here. It's going to talk about both. This is 2 samples. There's 2 ways to do that. You either use a between subjects design. So this is actually research design here. So this is something you would get into in a research methods class. So for between subjects, people are in one group or another. They can't be in both. So for example, with your RPs, which I haven't even opened, I'm sure they're fine. You're either in the terrorism word or you're in the police word, but not both. For repeated measures, that's when people take all of the study. So you're tested multiple times. So essentially, classrooms are giant repeated measures designs. Right? You're taking all of the tests. And the reason we go over that is because it matters when you get to running the statistics. So the research design often determines the statistic that you use. Okay, this is called the cookbook approach sometimes, which I have a friend, the first friend that introduced me to that was from the Netherlands. So they call it the kookboek. And I just, every time I'm like, can't help myself. But because what they're saying is like, if this design, then this type of test, just like it's like a procedure. So between subjects designs are independent T. That's the next chapter. Repeated measures designs are dependent T. I will warn you that they both have several different names. So repeated measures design sometimes is called paired T, sometimes it's called dependent T, Sometimes it's called repeated measures. Sometimes it's called within subjects. There are lots of names for this. It's horribly unfortunate. Between subjects designs are often just called between subjects or independent. But repeated measures, I think, has 4 names. I'm going to try calling repeated measures and dependency. So what do you have to do when you have people who are taking things multiple times? So this is a new problem that we have. And there are lots of problems that this causes, but the most important one is really order effects. So the order that you give people the levels, the different groups for the experiment, might change the scores. So the most famous case of this is this weight study. I think this is in like every intro book, where what they did was they had people estimating how heavy something was, so they were giving them weights and said, how heavy do you think this is? If they've got a 5-pound weight and a 20-pound weight, and they give you the 5-pound weight first, the 20-pound weight seems really heavy, because the 5-pound weight's kind of light. If we switch those, then the 5-pound weight seems really light, because you're holding the heavy one, and you switch to the lighter one, it seems much lighter. And if you've ever lifted weights and gone in both directions, you'll see this. So we have to control for that sort of issue. The other problem is fatigue. So if you're ever taking one of those surveys that has like 10 different questionnaires, and by the end you're just like, just end this thing. Those are called fatigue effects. So you don't want to stick the same questionnaire at the end every single time, because it's always going to be when people are tired. So what do you do? Well, the easiest thing is called counterbalancing. And now we can finally do random assignment. Like all year it's been like, can we do random assignment? Well, not really, there's one group. Now it's random assignment of which order they go into. So if you can control the order, put 1 before 2 and 2 before 1, then you can randomly assign. Okay. So we're not really assigning to groups, we're assigning to orders. Does that make sense to people? Groups, random assignment is the next chapter. You can't do that if it's a timed thing. So I can't randomly assign you to take exam 4 next. You'd be very unhappy with me, right? Because you'd be like, why is there chi-square on this exam? We didn't learn chi-square. Okay. So if it's a timed experiment, like that day 1 to day 7 thing that we did in the last quiz, you can't randomly assign. So if I can reverse the order, I can randomly assign and deal with order effects. If I can't reverse the order, then generally the question is about the order. All right, so that's called counterbalancing. So I have my little assumptions chart. So all the assumptions are the same for all of these tests. So we've got our 3 assumptions here, here, here. We're going to add 1 more here, and we'll get to it later. So the same 3 we've been doing, they're on the board. And the independency is going to have 1 more. So is the assumption, is it normal? So the question to ask yourself is, do I have at least 30 people, or did they tell me that it's normal? Every once in a while the problem's like, this is normal. I'm like, how do they know that? But so if I have more than 30 people, I can assume that it's normal. If I don't, I have to say, I don't know. Is the DV scale? If the DV is not scale, you can't really hit, there's no solution. You have to do a non-parametric test. And that question pops up again. I think a couple of them missed that one. Random selection or random sampling. We can't really do that a whole lot. We've talked about this throughout the semester, so instead maybe we can do random assignment. Maybe. Hopefully. So the question is still the same. Can I get to everyone in the population? So if you're talking about businesses and they have access to their entire customer database, yes. But then random assignment, can I reverse the order of these 2? Or for independent T, can I put them in either group? So if independent T, if it's gender, you can't randomly assign that. Right? All right, so we're going to get into paired samples T or dependent T. So it's a 2-sample mean and a within groups design. See, these are from the book, and they've already called it 2 different things. Right? So this is a dependent T, repeated measures design. It's sometimes called within groups. Okay, dependent T equals paired samples. repeated measures is often called a within groups design. This half repeated measures within groups is the type of research design. Dependent T, paired samples T is the type of statistic. They go together, they're not quite the same thing. Okay. All right. So we have 2 scores for each person. So one of the things that I did was I went ahead and uploaded the CSV, so you should see how it should look when you go to run this type of test. And how do we deal with having 2 scores? Because what we've been doing is having one mean. So here's my sample mean, here's what I assume the population mean is, what now? And the easiest thing to do is just subtract those scores. Okay. So if I create this difference score, if I take your exam 1 minus your exam 2, I can tell how many points you went up or down, or if you didn't change at all. Right? So a 0 score indicates that nothing happened, which is a good null hypothesis. So that's where we're going. And this should be the last column for this chart today. Just smearing it around. All right, so a z-score is a distribution of scores. Distribution scores. Okay, so that's the normal distribution, where each thing is an x. Then we talked about the distribution of means. Still a normal distribution, but now they're all samples. So remember, the distribution of means is skinnier. That's that video, distribution bunnies video. Still z. Last week we talked about t. It's a distribution of means still. Because we got one sample, we're still testing sample means, but we don't know the standard deviation. And then this one is going to be a t of mean differences. So the distribution of differences between means. Okay, both of these. And I wrote this kind of differently for a reason. So for dependent T or pair T, it's mean differences. So the difference between time 1 and time 2. Okay. For independent T, it's differences between means, and that seems like just slightly semantic, but differences between groups is really what they mean. Whereas the dependent T is differences between the same person twice. And that just highlights the difference between the type of design we're talking about. Because in the math between these two, while on the formulas don't look so different, very different. Yeah?
So is this I can't think of the exact terms, but the difference between like a longitudinal study and, I can't think of what the other one was.
Cross-sectional.
Cross-sectional, yeah.
Yes.
So like dependent would be longitudinal, and then
right. The independent would be cross-sectional.
Okay.
Right.
Yeah.
I mean, they're very simple because you only have 2 groups or 2 test times, but yes.
Okay.
Repeated measures anything. It's not anything over time. We have an example where it's not quite time, but time is always a repeated measures design if you're testing people multiple times. Okay. So for example, on the Word doc, the first one is about the rec center, because when I made this example, they had just finished the rec center. So comparing the old rec center to the new rec center. So that's not really time, but you're comparing 2 different things. So we asked every person both. How do you like the old one? How do you like the new one? But on this one, it is time. So anytime you see before and after, it's automatically dependent T. Yeah. So why I talk about this distribution thing, and I think it's important to highlight what we're still interested in. So we're still interested in this top piece here. So x minus the mean, we assumed the null was 0. So there's no difference between the person and the mean. the null would be a 0. There's no difference between the sample and the mean, the null would be 0. There's no difference in times. So the old Breck center to the new Breck center, the subtraction would equal 0. And so what that top piece does by subtracting is it creates a distribution, so just a fake example here, where most of the data is centered over 0. So we talked about z-scores being the best thing since sliced bread because they were standardized, and that meant the mean was 0. Yeah? Did you get it? Yes. Okay. Okay, so z-scores are really great because they're standardized, and the mean of them is 0, which makes a 0 a useful number. T is the same way. It's standardized so that the mean is 0. That also implies, now this was on the last quiz for no good reason. But what does T mean? Okay, so it's the distance from the mean in standard error units. I think this was on the quiz Friday. It was mainly asking you about the formula. But if I think about z being the number of standard deviations away from the mean something is, t is the number of standard errors away from the mean. And that's a null mean of 0. So how far away from 0 are we? So this is in stats. If I had to think about t, like explaining it to somebody who doesn't speak statistics, I would say how far, oops, that's not far, from 0 is my score. So big numbers are further away. And so the nice thing about t is it's still standardized. So we spent a lot of time talking about how z is standardized, and that makes these nice pretty percentages easy to calculate. T is the same way. Remember, t and z are often the same if you have 100 people, right, or more. So I can think about t as being how far away from 0 is my score. And I want it to be farther away from 0 if I want it to be significant. Okay. But it's standardized in terms of the sample, because different sample sizes change how t looks. Okay. And that's why the cutoff scores are different every single time. That should be all the theoretical mumbo-jumbo. Hopefully. Okay, so why use this differences between means, where this is what we've just been talking about. We're still talking about t. And the comparison distribution, anytime you see comparison distribution, they're talking about when the null is true. Okay. So that creates a mean, an estimated population mean of 0. So in all of these, I lied to you, one more column. These three. You define what the sample, the population mean is. Okay, it's 20, it's 30, it's 10. But on these two, we're usually assuming that mu is 0. Usually, not always. 99.97% of the time, people assume mu is 0.
So is a lot of times what we're doing with the t test, is it pretty much that we're just forcing it to be a ratio variable, like versus, I mean, because you may start with a ratio variable, but like you're forcing it to have a meaningful 0.
Yes.
That's centered around
Yes.
the mean that you found.
In essence, all of this is log odds. So the odds of the difference being greater than the error.
Okay.
So we want a big ratio. The odds of our good variance, the experiment working the way we want it to, over error, should always be big.
Okay.
Right?
Yeah.
So we want mean differences to be much larger than error. But by subtracting the means from each other, we do create a meaningful 0. Yes, that's the point I'm trying to get to here. So then we can use our distribution, right? And so if your score is close to 0, that means essentially nothing happened. It didn't change from time 1 to time 2. The further away from 0 it is, the more change that you see. Now, the cool thing is, if we have a set of difference scores, So we go from having 2 columns to 1 of just difference scores. It's single sample t. Woohoo! That means the steps are the same. Yay! So dependent t is single sample t with on the difference scores. Right. And that's why these 2 chapters are together. And then independent t is its own nasty set of math. So let's try one. And that's all the steps together. We're going to work through them one at a time. Because everybody got the crazy chart on the board? I'm just going to smear it around. And hopefully you'll still be able to read. Just like I think 1 class in front of us this morning. How did they make such a mess on this board? Okay. So let's look at this first example about the rec center. So here, I'll just type because this, like, y'all are going to be able to read that. So, all right. So we're examining our student satisfaction on a 1 to 5 scale. So this isn't ratio, but it seems at least interval. Higher numbers are more satisfied. With the old rec center, are we at the point where you guys have never seen the old rec center? Oh, good. It was awful. And then the new one with the fancy pool. I think we made times or something about how fancy it was. It was funny because that and my old university were both in there. Both places I had left right before they finished. So we grabbed random students and asked them, so are we more satisfied using P less than 0.01 here? And we're going to list the 6 steps. Okay, so here's the data. So our first assumption is the DV scale. This way. So you want to hear me typing? It's probably interval, so yes. So a 1 to 5 scale is not ratio, but it's least interval, so we're okay. Can we, well, let's do normal. Unlikely. I don't know. We only have 7 people. So I know you guys were joking the other day about how n is always 15. So when I looked at my example on the homework and they had 15, I had a good laugh. But this is only 7. Can we randomly select? Well, kind of. Maybe. I mean, we do have access to the entire population, but more than likely what they did was just scratch people as they were walking out of the gym. Right? So we can't take everybody at the university, because some of you have never seen the old one. Some of the students who graduated have never seen the new one. So we've got like a slice of students that did use both. But we can definitely randomly assign to what order we ask them in. How do you feel about the new one? Okay, how do you feel about the old one? And then the next person we can flip it. Okay, how do you feel about the old one? How do you feel about the new one? So we could randomly assign to order. Alright, so see, those are still the same. So this is a little bit of a tricky part. The sample here it's still one sample. So we have to try to put the sample all on the left side. So it's actually, the sample is going to be the difference scores. So don't put it as old versus new, okay? Because that implies that there's 2 samples. Really what we're asking about is the difference between old versus new different than 0? So our sample is going to be our difference scores. So we're label our research in a null. So the difference in old and new feels, right? So the DV is their feelings. Because that captures what the sample actually is. So we're looking at if there is a difference between their old and new ratings compared to a population where there would be no difference. So you're kind of saying, is there a difference versus no difference? As this to me is a little awkward. But try not to write it as old versus new, because then you'll get this one and independent T confused. So the population is going to be no difference in old. New. So essentially what we're saying, the population is mu is 0. So we've got our different score for our sample versus a population of different scores that are 0. And what we're wanting to find is if they're more satisfied with the new facilities. So what we'd want to do is, like, that makes more sense to go, the different score would be greater than 0. And then this different score will be less than or equal to 0. The tricky part about that, oh right, this is the crappy pen. Try again. Is let's say the new score is 4 and the old score is 2, just for fun. If we do old minus new, we're going to get a -2, right, mathematically. If we do new minus old, we're going to get a +2. So what you have to be careful with is which order you subtract them in, given what you did here. So I expect the scores to go up. I expect the new ones to be higher. So I'm going to put new first, so that positive numbers mean higher. And when we do this, when we type this out into R.
Is that why there's that crazy R code for like switching, like, because occasionally like there'll be ones who don't match the trend and some of them turn out negative.
Oh, you're talking about reverse coding.
Yeah.
Yeah, for questionnaires. Yeah, if your entire question is positive and you have 3 reverse questions, you want to reverse them first.
Yeah, so that's what this is.
Kind of. This is making sure you have them in the order that of your hypothesis you expect. So this is often why people don't do one-tailed tests. We've talked about how they're cheating, right, power, but also because of the subtraction thing. So if you always do a 2-tailed test, you don't have to think about the subtraction. But we're trying a one-tailed test. So I want to make sure that we expect new scores to be higher, so I'm going to do new minus old. And I can just make that note to myself. New should be higher, so we're going to do new minus old. Okay. You don't have to include that when you're writing them up, but if it helps you think about what that means. Because if we did old minus new and we got a negative number, we would probably fail to reject even if we were right, just because of the way we subtracted them. I'd say that's probably the hardest part. So let's import the data and see if we can calculate some of these scores. So we're going to get a mean difference score, because that's what we're really interested in, is how different are the scores from 0. And then the standard deviation of the differences and the standard error of the differences. So that denominator is about the different scores. When we get to independent T, the denominator is an average standard deviation, in a sense. So dependent T is all about the different scores. Independent T is all about how different our two means. I know that's like just it sounds like I'm just rearranging the sentence, but they're conceptually very different. Right? So I'm going to subtract me from myself and create a different score for only me. Whereas independent T is I'm subtracting my group from your group. Okay. So this is chapter 10, no number, online. So you'll want to import that data. There we go. So I'm going to go import from text file. Ooh, where did I hide it? The desktop, I think. Chapter 10 data. You can call it whatever you want. Okay, but it should have a header, so you have them next to each other. Okay, you want to keep them next to each other. You don't want to stack them. And we're going to hit OK. So we should have data that looks like this. So in this instance, this is called wide format. We've talked about this very briefly when we did graphs before. Right. So wide format is where each person gets their own row. That doesn't really work for graphs. So when you're making something like this in ggplot, we had to melt the data and rearrange it a little bit. But it does work really well for dependency. So we're going to leave it in wide format. And use that to create our scores here. All right, so we're going to create a mean difference score first. So this is where I'm saying, if you think about your hypothesis and you pick a one-tailed test, the order of the subtraction is important. So we kind of went over that already. So we're just going to create a difference score. And we haven't done this $ thing in a while because I know I got a couple of emails from you guys about RPE3. So remember, when you have multiple columns, you have to tell it what data set it's in and then what column it is. Oops, sorry. Right. So what we're going to do is create our difference score. And I've just called mine chapter, I just let it import, it's chapter 10 data. And my $, we said we'd do new first, so I'm going to do new. Minus chapter 10 data, $old. So this will subtract each person from every other person, or each person from themselves, rather, sorry. And creates you a column of the differences. If you aren't sure about the order, you can always click on the data set to see it. Okay. And I'm expecting new to be higher. So 2 minus 4 is going to be a negative number, so I want to make sure I do new first in this example. Now you can apply everything we did last week to that set of scores. Okay, so there's one extra step. So to get the mean, we're going to do summary of the difference score we just made. So our sample mean is 0.86. Our standard deviation, so I'm going to do SD of the different scores, 1.07. So I need the mean difference for both the test statistics, so step 5, and for effect size. Okay. The standard deviation I need for the effect size. The standard error of the distance, or SM and S in the notes. Just gonna try to use both here. Standard error of the difference, we're going to divide by the square root of n. Or we can use our big formula that we've been doing. It's 0.40. Now, a quick note on this square root of n thing. So the formula is still standard deviation divided by the square root of n, which is nice because it's been that this entire time. However, don't be confused with n and then the number of scores. Okay, there are 7 people in this data set. They're tested twice. So n is number of participants, or number of lines. So that's 7, not 14. Because there's 14 scores, but only 7 people. And so that's why I would always tell you for dependency to set it up in this way. Because it's clear there are 7 people. When we do independency, next week we'll talk about how to make it look different so that you don't get the two confused. There's only 7. So we took 1.07 divided by a square root of 7, and then got 0.40. So this pretty much ensured that I couldn't screw that up. So they're not 14 scores, they're 7. That is one of the questions that it'll try to, on the multiple choice questions, and they give you an example of one filled in. Make sure you're using n and not number of scores. Okay, where are we at? We good? Do we have everything? Oh, so the next thing to write down is n, actually. So 7. Okay, so I have 7 pairs of scores. Oops. All right, so what does that make degrees of freedom? 6. Good. It's still a -1. Woohoo! For one more week, anyway. I think it's because we get to this point and everything's like, okay, this is similar and similar and similar, and the independentity is similar-ish. There's like just enough different that you're like, what? So I'm trying to prime you. And I know this has been a touch confusing, so I tried to really make sure it was clearly laid out on this slide so that you had it written a couple of ways. So this is actually true for single sample t as well. So if you're using a less than test, it's going to be alpha, so 0.05 or 0.01, depends on the problem, the note is about here. Degrees of freedom, lower tail is true. If you have a greater than test, its lower tail is false. If you have a difference test, not equal to test, that's when you're going to divide by 2. So I might tell you, when you're studying for this test, this exam, this test table is really great. That looks crazy. What you might do is maybe change out some of this. This isn't helping you to include those little pieces. Like which one you use. Okay, so where are we at? Here we have a one-tailed positive test. So we're going to use QT. It's actually 0.01 in this example, right? Yes. So I've got 0.01. I don't have to divide by anything because it's a one-tailed test because I've got just greater than. Degrees of freedom we decided were 6. And it's a positive test, so lower tail is false. Got 3.14. Now, this is where they should match. This is a positive number. This is a greater than test. Okay. If you have a less than test, it should be a negative number. If you have an equal to and not equal to test, the difference test, you should have 2, because there's both positive and negative. Okay, so make sure it matches step 1, 2. Make sure it matches step 2 as well, rather. Okay. Step 5 is where we're going to actually get T. Now you could do a single sample test on the different scores, so you could use the code from last week. I went with the code that's actually for dependent T, because when we get to independent T, it'll match a little better. So we're going to do this type of code. Okay, but there's more than one way to run this test. So let's do T.test. We're going to go back to the original data set in the same order that we did this step. So our chapter 10, I'm going to use new column first, and then it'll subtract in the same order, and then do old. So I did the order exactly as the same as I did this difference score thing. And then we did last week, we did mu equals 0, but that's assumed, so we're going to drop that. Then we've got this paired equals true. Okay. If you use mu equals, it assumes it's a single sample test because you only have one column of data in there. If you have 2 columns of data, so we have a new and an old, it's kind of like, okay, you want an independent T or dependent T? Okay, the default is independent T, and you'll get the wrong answer. So be sure you have paired equals true if it's dependent T. And then our 2 lines we used before. So our alternative here is greater. Conf level is actually 0.01. Oops, sorry. 1 minus 0.01, so 0.99. Okay. So remember, P less than 0.01 is a 99% confidence interval. I don't know why we can't all keep it in the same direction, but I don't make up the rules. So. All right, all that typing, let's run that. So I think this is the problem I did, yeah. I did a 95% confidence interval because I wasn't paying attention. So we'll get slightly different numbers here. Get this on the next page here. Okay, so what do I need out of this? Well, I want T. So I'm going to check and make sure my degrees of freedom match. They do. I had that right. Cool. I want to make sure my mean difference score matches. 8.86. It's in the same direction I did it a minute ago, so it's positive, which is what I was expecting. Awesome. But the only number you need for here is this T. So is T significantly different than what we would expect? We went with P less than 0.01. So is it greater than 3.14? No. So we said the finish line is here, 3.14. And we go home happy. Yay, happy out here. Anything over here, sad face. Don't reject. Fail to reject. We only made it 2.12. So if we're using 0.01 as our cutoff, we're going to fail to reject. So, is your score more extreme? You would reject the null. Your score is closer to the middle, closer to that 0, you're going to fail to reject the null.